Hi again, everyone. This is Professor Sebastian. Welcome back to our Calculus 3 class notes. We're on page 69 in section 14.7. And we're talking about extreme values, and we're going to get to what's now known as the saddle point. So make a note here that a differentiable function f of x, right, a function of a single variable, might have a point of inflection at a critical point. So that's a point where it changes in concavity from concave up to concave down or vice versa. Whereas a differentiable function f of xy might have what is called a saddle point. So now here's the definition of a saddle point. A differentiable function f of xy has a saddle point at a critical point AB if in every open disk centered at AB there are domain points xy where f of xy is bigger than f of AB, and there are domain points xy where f of xy is less than f of AB. So these points AB, f of AB are saddle points up the surface z equals f of xy. So let's look at a simple example first, then I'll show you some more complicated saddle points. Okay, example 55. Find the local extreme values, if any, of f of xy equals y squared minus x squared. So the solution, domain of f here is the entire xy plane, has no boundary points. So the partial of f of x, partial of f with respect to x equals minus 2x, set that equals 0, you get x equals 0. Partial of f with respect to y equals 2y, set that equals 0, you get y equals 0. So a local extrema could occur at 0, 0 with the value of f of 0, 2, which is 0. 0, 0, that should be f of 0, 0, right? It occurred at 0, 0, this should be f of 0, 0, which is 0. All right, however, along the positive and negative x-axis, f of x0 is minus x squared. Right? Along the positive x-axis, f of x0 is minus x squared, right? Because along the positive x-axis, y is equal to 0. So you can kind of see that minus x squared right in here, which is an upside down parabola, right? Along the positive and negative y-axis, f of 0y is y squared, right? When x is 0, 0y squared along the positive and negative y-axis. So there's that parabola. So you can imagine this point right here is not a minimum or maximum. It's called a saddle point. It's named saddle point because it looks like it's really named after this function, this hyperboloid here, because you can imagine sitting on it and holding on to the what's this called, the crown of the saddle. You're sitting with your legs straddled across, so it's called a saddle point. And then every open disk in the xy plane centered at 0, 0. So every open disk right here contains points where both the function is less than 0 and where the function is greater than 0. So there's a saddle point at that point.